The next talk will be by Professor Ritabrata Munshi. Professor Munshi is at the Indian Statistical Institute in Kolkata. And before that, he was faculty at the Tata Institute of Fundamental Research in Mumbai. He works in analytic number theory, having received his PhD at Princeton under Andrew Wiles. Following that, he was an instructor at Rutgers, working under the supervision of Hendrik Ivanic. Ritabrata is best known for his groundbreaking theorems on estimates for L functions that supersede convexity bounds. His work has been recognized with the Bhatnagar Award in 2015, election to the Indian Academy of Sciences in 2016, the Infosys Prize in 2017, and he was an invited speaker at ICM 2018. Ritabrata is obviously not able to be with us in person. I believe he's speaking from Kolkata, is that right?
Yeah, that's right.
Yeah, so Ritabrata, take it away.
Okay, thank you, Kumar. And I'd like to first thank the organizers for their kind invitation. And I really wanted to be there in the Fields Institute. This is the third time I've got an invitation from the Fields Institute, and this is the third time I'm not able to be there. My visa application got stuck somewhere in the pipeline. Anyway, so today we are celebrating 100 years of the 1924 ICM held at Toronto, and 100 years of the concept of Fields medal, an award which has played a significant role in the development of mathematics in the last several decades. Okay, so my topic today is circle method and some recent applications of the circle method in the field of towards analytic theory of automorphic forms and their L functions. Okay, so well, the concept of circle method is also like 100 years old, so it's a little more than 100 years old. That's right. It was introduced in a paper of Hardy and Ramanujan, which is this one, asymptotic formulae in combinatorial analysis. In this paper, they came up with an asymptotic formula for the partition function Pn. Okay, so recall that the partition function Pn is the number of ways of writing n as sum of positive integers. If you look at the generating function for the partition function, sum of Pn x to the power n, then it's very easy to show that it's given by the reciprocal of this product. And if you expand, then this is given by this series in the denominator. All right, you can surely easily relate this to the Dedekind eta function. So in particular, you can show that this is giving you a holomorphic function in the inside the unit disk in the complex plane. And so to get Pn, we can just use Cauchy's theorem. So that's what Hardy and Ramanujan did. So they used Cauchy's theorem. So they took a circle inside the disk and integrated fx by x to the power n plus 1 on the circle, and that gives us the partition function Pn. Okay, and then they realized that to evaluate this integral, the main contribution in this integral comes from the singularities of fx. The points. So if you take the circle bigger and bigger and go towards the the unit circle, then the points which are near the singularities of fx will give you this major contribution, and the points which are away from the singularities will give you a smaller contribution. Okay, so you can see from the generating function over here that 1 is kind of a singularity for each of these factors over here: 1 by 1 minus x, 1 by 1 minus x squared, 1 by 1 minus x cubed. So 1 is kind of the heaviest singularity that you have of the generating function. The next one is minus 1, because minus 1 is a singularity of 1 by 1 minus x squared and every even term in this product. And then you have the third root of unity, and then the fourth root of unity, and so on and so forth, right? So now if you, so near this singularity, so this is the unit circle over here, this picture. And the blue color over here gives you the size of the singularity over that point. Okay, so the big blue blot over here says that the singularity at 1 is really heavy. Then the next heaviest one is at -1, and the third one is at the third root of unity, and so on. Okay, near the singularities, if you take x to be r times e to the power 2 pi I p by q, where r is the radius of the circle that you are taking, and so r is going very near 1, then at this point, you can estimate, or you can give an asymptotic expansion of the generating function fx. Okay, so Hardy and Ramanujan use the automorphy of the Dedekind eta function to come up with this asymptotic. So fx is asymptotically exponential of this. And using this, they prove that the partition function Pn is asymptotically 1 by 4n square root of 3 exponential of y square root of 2n by 3. Okay, so this is basically the sketch of the Hardy Ramanujan circle method that they use to give an asymptotic for the partition function. Well, as it turns out that if you go back to some of the letters that Ramanujan sent to Hardy, even before going to Cambridge, then this is the page number 7 of one such letters. And in here, you can see a series of formulae, Ramanujan's usual style. And here I want to focus on the last formula over here, okay, which is given something in the chat. Oh, sure. Okay, I'll try to speak a little louder. Okay, the coefficient, so the last formula over here, number 7, says that the coefficient of x to the power n in this 1 by this power series is the nearest integer to this. Okay, and you can see that this is very similar. This is very similar to the power series that we have in the denominator over here. And the asymptotic over here is quite similar to the asymptotic of the partition function that the Hardy and Ramanujan got over here. Okay, so so Hardy actually in his obituary that he wrote after Ramanujan's death mentions this, and he writes that after that there is always more in one of Ramanujan's formula than meets the eye. Anyway, Ramanujan passed away in 1920, but between 1920 and 1928, Hardy and Littlewood wrote a series of papers on the circle method. They basically developed the circle method, and they introduced the most important concepts in the circle method. Okay? So if, for example, the major arc, those are the small arc around the singularities, which will give you the main contribution to the asymptotics. And then the rest is called the minor arc. Okay, those are the points which are away from the singularities and on which, and the contribution of which will be giving you the error term. And basically, while estimating the function on the minor arc, you use some sort of estimates for exponential sums. For example, Hua's lemma, or you try to use Weil differencing, something like that. Okay, the other concepts that they introduced is this concept of singular series and singular integral. They showed that the major arc contribution, where you can write it as an asymptotic, and the asymptotic actually breaks down as a product of a series and an integral. The series is called singular series, the integral is singular integral, and the singular series further breaks down into a product over primes, giving you the local densities of the number of solutions. Okay, and the most important contribution, I think, of Hardy Littlewood in this case is that they realized that the automorphy of the generating function is not an essential requirement. Okay? As long as you have a way to write down an asymptotic expansion near the singularity of the generating function, you can work it out using the circle method. Okay, so the Hardy-Littlewood circle method works best for additive problems. Okay, this is where they actually developed this method. So this is the general additive problem. So you take an increasing sequence of non-negative integers. Let's call it A. And let RRn is the number of representation of any integer n as a sum of R members of this sequence A. Okay. So we can define the generating function fz to be this sum, z to the power m, this formal sum. Then if you take the rth power of fz, then you can see very easily that it gives you the power series whose coefficients are exactly the number of representation of n as the sum of R members of A, so RRn. So we are mainly interested in estimating RRn, or try to give an asymptotic formula for RRn as n goes to infinity. So that one can get a formula for that if one knows something about the analytic properties of this generating function. Okay? Again, by Cauchy's integral formula, we can write RRn as this contour integral. And again, the main contribution, the major arc, is given by the points near the singularities, which are given by e to the power 2 pi I p by q with q small. Okay, and the rest is the minor arc. So this is the basic setup of circle method. And here are some examples. So first of all, this is the classical varying problem, where you take the sequence to be the kth powers, and you want to show that for every integer n, if you take sufficiently many kth powers, then that integer can be written as a sum of those many kth powers. And yeah, so that those there is a gk, which gives you the minimum number of kth powers that you need to get all sufficiently large integers as a sum of those many kth powers. Okay, so that's one thing that fits nicely in Hardy-Littlewood framework, and this was one of the focus problem that Hardy and Littlewood were trying to solve. The other one is the Ternary-Goldbach problem, where you take A to be the set of prime numbers, and you take R to be 3. Okay, so you take the set of A to be the set of prime numbers and R to be 3, then Rn here is a number of representation of n as a sum of 3 primes. Okay. So you can recall that the original Goldbach problem is about writing integers or even numbers as a sum of 2 primes. And this is the ternary version of that. It's where you are trying to write every odd number as a sum of 3 primes. I guess actually this is the problem that was originally posed by Goldbach, and Wheeler came up with the 2 prime version. The other applications that one can get from Hardy-Littlewood circle method, it's the theorem of Roth, for example, which says that any subset A of this sequence 1 to n, containing at least n by log n many elements, will have a 3-point arithmetic progression. Okay, that's Roth's theorem, which is also a nice consequence of Hardy-Littlewood circle method. There is also this Davenport-Heilbronn theorem, which is about if you take lambda 1, lambda 2, lambda r to be non-zero real numbers, not all in rational ratio, then if you look at this combination, you can make it very small for any eta. Okay, and also the theorem of Bartsch, which is about counting rational points of a given height on varieties. Okay, so if you have a set of polynomial equation, and if you take the variables in a box, and you want to find out how many integers are there which satisfy that system of polynomial equation, then you can use Bartsch's theorem or Hardy-Littlewood circle method to come up with an asymptotic, as long as the dimension or the number of variables is much more compared to the degree of the variety of the degree of the family of equations that you have. Okay, so these are the some of the examples of classical applications of the Hardy-Littlewood circle method. And so the modern viewpoint, the circle method is actually some sort of a Fourier expansion of this delta function. So delta n is defined as a function over integers, and delta n equals to 1 if n is 0 and it is 0 otherwise. So it's just determining the event whether the integer n is vanishing or not. And in circle method, what you try to do is you try to come up with a Fourier expansion of delta n. Okay. For example, if you look at Vinogradov's version of the Hardy-Littlewood circle method, then it actually evolves from this this identity that delta n is the integral from 0 to 1 of exn, where ex is the exponential e to the power 2 pi I x. Okay, so yeah, so delta n is given by, this is an integral representation of delta n. And then in Hardy-Little circle method, you split the integral into two parts. This is the major arc, this is the minor arc. So here you put those points which are very near to rational numbers, which has small denominator, and that will give you the major arc. And the rest of the circle goes to the minor arc. Okay, so that gives an expansion of delta n, right? And so this other version is given by Klosterman, which is another version of Hardy-Little circle method without minor arc. Where what happens in Klosterman's formula is that you expand the major arc a little bit using Faraday dissection so that you can absorb the points in the minor arc in them. Okay, so but when you use the Faraday dissection, the length of the arcs are not fixed. It depends upon what Faraday point you take. And so to see the length of the, to keep a track on the length of the arcs in the major arc, you need to introduce what are called the Klosterman fraction, this type of things, a bar n by q. Okay, so this is a clean Fourier expansion of the delta function. Okay. So here you can take, so q, capital Q is a parameter which is up to your choice. And you can, depending upon the problem that you are attacking using the delta method, you can choose capital Q wisely. And so there are two parts in this formula. So if you look at a bar n by q, this is the arithmetic part of the exponential, and nx by aq, where x is involved in this integral over here, is the analytic part. So it's an arithmetic oscillatory term times an analytic oscillatory term, right? All right, so one modern version of delta method or circle method, which is called the delta method, is the following. So here, this was introduced by Duke, Friedlander, and Ivanich. And the idea is that an integer is 0 if and only if it is divisible by every integer d. Okay. Starting with this, so this is kind of, it's a very different starting point from this integral representation. But yeah, starting from this, do a little bit of manipulation, then you end up with such an expansion of the delta. So delta n, so there's still an integral over here. It's a little longer than 0 to 1. You can throw in a smooth weight. So GQX is a smooth weight. You'll have a control on its derivatives. You may also write it down explicitly, but it doesn't help that much. The nice thing is if you compare this version of the delta with the Klosterman version of circle method, then you can see that, so here the disadvantage was that the arithmetic variable a is also involved in the analytic oscillatory part. Okay, and that is not so in this, in Duke, Friedlander, Ivanich delta method. A is the arithmetic variable, which is this a bar over here is playing the role of a bar, but this a is not involved over here in the analytic oscillation. So in Duke, Friedlander, Ivanich approach, the main advantage was the analytic oscillation was completely disjoint from the arithmetic oscillation. Anyway, so that's, yeah, so Duke, Friedlander, and Ivanich used their delta method to study the shifted convolution sum problem. Okay, so consider lambda fn plus hq. So h is some fixed number. You can take h to be 1, for example. So it's basically lambda fn plus q. And n has length capital N. So there may be a smooth weight over here. I'm ignoring that. So n is basically ranging from capital N to twice capital N in a dyadic segment. And these lambda f's are the Fourier coefficient of a modular form here. You can also take mass form. In their original paper, they were only considering modular form. So let's stick to modular form. So take fz to be, so the Fourier expansion of fz is lambda fn. So these are the normalized Fourier coefficient. Okay, so lambda f1 equals to 1, and the bound for lambda fn is tau n, the divisor function. ENZ, so it's e to the power 2 pi INZ. And since since Q is not equal to 0, okay, so it's a non-trivial shift, you expect that there will be no correlation between lambda Fn and lambda Fn plus Q. So there will be no conspiracy in the way they're oscillating. And so the oscillation of lambda Fn and the oscillation of lambda Fn plus Q will not cancel each other. And so there still be a cancellation in this sum. Okay. So that's what Dirichlet-Ivanich proved, that there is a non-trivial bound for such sum. And this shifted convolution sum actually originates if one studies the second moment of the L function at the central point of f twisted by chi, where chi is running over characters modulo q. Okay, and in DFI, they had to introduce an amplifier, because even if you get an asymptotic for this, you'll not be able to get subconvexity, because so the main point of their paper was to get a subconvex bound for L half f twisted by chi. And so chi is modulo q, so f cross chi has conductor q square. So the convexity bound of L half f twisted by chi is like square root of q. And you want to bid that, so that's getting subconvexity. So even if you have an asymptotic for this, the asymptotic at best can be some constant times q plus some smaller order terms. So from there, the best bound that you get is that lambda L half f twisted by chi is like square root of q, which is the convexity bound. So the second moment will not give you a subconvex bound, and we know that in such situation, the standard idea of Ivanich is to introduce an amplifier, and that's called the amplifier second moment. And what the amplifier does is it amplifies the contribution of one particular character chi, which you are interested in, and since it amplifies that contribution, you get a better bound for that particular L function. Okay, and this way they got a subconvex bound for this twisted L function. And this was required to prove a theorem, problem of Linux about distribution or equidistribution of rational points on sphere. Okay, and later Heath-Brown used the same delta method to count rational points on quadratic hypersurfaces. So hypersurfaces are given by such an equation. So Heath-Brown applied this modern version of delta method to settle a more classical problem. Of course, this type of quadratic forms were already covered by Bartsch's theorem and the result of Klosterman, but this is a different approach. Okay, so there are 2 points to notice over here. One is that Dirichlet-Ivanich applied their newly formed delta method to attack a problem which is still an additive problem. Okay, so the problem over here, the shifted convolution sum problem over here, is an additive problem. Okay, it's like the additive divisor problem, which is the classical problem of asymptotically evaluating dn plus 1. So it's a additive problem, which was the case also in the Hardy-Littlewood circle method. And the other thing to notice is that so if you compare the Klosterman formula or the Hardy-Littlewood formula with the Dirichlet-Ivanich formula, you will see that the harmonics that they are using over here are all the harmonics coming from the circle group. So they are all trigonometric polynomials. So there is no new harmonics in this version of the delta method. Anyway, so we want to extend the range of application of this delta method. So we want to look at what we call the correlation problems. So suppose you're given 2 sequences, 2 arithmetic sequences, an and bn. We want to understand the sum an times bn. Right? And so usually in the problems that we try to solve, the sequences have these properties. Okay, so first of all, we can assume that an and bn are finite sequences. They are supported in some dyadic range between capital N and 2n. We can assume that the ANs and BNs are bounded by n to the power epsilon. If not pointwise, at least in the L2 sense. That is, if you take the sum of mod AN squared, that will be bounded by n to the power 1 plus epsilon, and so on. And that at least one of the sums, a sum of AN or sum of BN, is small. That is, there is some cancellation in one of these sums, say, of size n to the power 1 minus theta. Okay. Then the correlation between the sequence AN and BN, if you use the standard definition from statistics, then this is the mean of the product minus the product of the mean. So that gives you the since one of them is quite small by our assumption, so this is like S by N. So S by N plus big O of n to the power minus theta, right? And we say that these two arithmetic sequences are theta independent if this sum is bounded by n to the power 1 minus theta. So trivially, this is bounded by n. If we have a cancellation by this magnitude, then we say that these two sequences are theta independent. Okay. Now, there are several problems in analytic number theory and beyond where such a correlation problem appears. For example, the classical Dirichlet divisor problem or the Gauss circle problem. So the classical Dirichlet divisor problem is about the asymptotic of sum of the divisor function. So sum of dn, n going up to x. It's easy to write down the main term. The main problem is to get an estimate for the error term. And Dirichlet proved that the error term is like square root of the main term. Over the years, that has been improved, and we know something better than x to the power 1/3. And it was conjectured, it has been conjectured that it will be like x to the power 1/4 plus epsilon. So that's the Dirichlet divisor problem. A similar problem is Gauss circle problem, where you want to count how many lattice points are there inside a circle. So take a big circle on the plane of, say, radius n, and try to count how many lattice points are there inside that big circle. And it turns out to be quite similar to the Dirichlet divisor problem. The third problem is about critical zeros. So this, of course, the famous Riemann hypothesis says all the zeros of the Riemann-Zeta function, non-trivial zeros of the Riemann-Zeta function, are on the critical line. And of course, the generalized Riemann hypothesis, which is expected to be true for all automorphic L functions, says that all the non-trivial zeros of automorphic L function should be on the central line. Okay, those we call critical zeros, right? We don't know Riemann hypothesis for even a single L function. But from a theorem of Hardy shows that there are infinitely many zeros of the Riemann-Zeta function on the critical line. In fact, you can actually show that they are positive proportion. And as far as I know, it's now like 42% of the zeros of the Riemann-Zeta function are critical. They're on the central line. The same can be proved that there are positive proportion of zeros for any GL2 L function. And but nothing is known beyond GL2, right? So if you start with an automorphic representation of GL3 and look at the corresponding L function, it's not known whether it has infinitely many or if it has any critical zero. Okay. So with the knowledge there is really lacking. Okay, you may study like additive divisor problem or moments of L functions and subconvexity problem. Okay, so all these are related to finding correlation between two different sequences, right? So let's see. So if you look at the Dirichlet divisor problem, then the correlation problems related to that is given by this. So it's a dn is the divisor function, and it's a divisor function twisted by e of square root of n x to the power 3, where here n is ranging between x and 2x. So here you have an oscillatory term where the amplitude of oscillation is like x squared. And this is a GL2 object. So the conductor is like x to the power 4. And related to that, you have a very short sum. And if you can improve, if you can get a non-trivial bound for this, then you can get a bound better than x to the power 1/3 in the error term of Dirichlet-Divisor problem. Now, the Dirichlet-Divisor problem can be extended to the cusp forms. So you can, instead of the divisor function, which are, you can think of the coefficients of the Eisenstein series, you can replace it by the coefficients of a cusp form, lambda Fn. And again, so here also we are looking at the sum of lambda Fn, where n is going up to x. And of course, there is no main term, unlike the divisor function. But the error term is expected to behave in the same fashion. So you expect that the error term will be like x to the power 1/4 plus epsilon. Again, what we know is x to the power 1/3 plus epsilon. That is coming from the Voronoi summation formula. And any improvement or any non-trivial bound for this correlation sum will give you a non-trivial improvement of that bound. Okay, so for a long time, the Voronoi barrier has remained unchallenged. Okay, so now here is that the thing about critical zeros. So you start with a GL3 automorphic form pi, and if you look at the L function, if you want to show that there are critical zeros, then the correlation problem that pops up looks like this. So you have a pi n1. These are the Fourier coefficients of this form pi. And then it's twisted by this phase function, okay? And now you see that, so here n is of size capital N. So this amplitude of this phase is like n to the power 2/3. Since it's GL3, the conductor of this sum is like capital N square. And you have a length of size capital N, which is like square root of that. So it's almost like a subconvexity problem, getting a non-trivial bound. But to get critical zeros, you need not an epsilon independence, you need a 1/6 independence. So yeah, so here you need a saving of at least 1/6. So instead of theta independence, you need 1/6 plus epsilon independence in this case. So you're asking for a bound for this, which is of strength of subwhile. And as you know, that subwhile bound for L function is very rare, and it's only known in certain cases for like the Riemann zeta function or for some prime power, characters of prime powers. Okay. The next one is a subconvexity problem. So for example, if we consider, it should be L half F twisted by chi, right? The L function that was considered by Duffield and Ivanich in their paper. So they proved subconvexity going via the shifted convolution sum. But if you use the approximate functional equation directly to L half F twisted by chi, then you come up with sums like this. And showing us, proving a subconvex bound for this is same thing as proving a non-trivial bound for this. So it's again a correlation problem between the Fourier coefficients of a GL2 form and a Dirichlet character. Okay, so the main difference between all these problems and the problems that we had before, that they are all additive problems before, and now they're no more additive. They're all actually multiplicative problem over here. Okay, so usually these are beyond the usual form of circle method or delta method. So you need to do something with the delta method to tackle such problems. Unfortunately, so far we don't know how to deal with this problem for Dirichlet-Divisor or critical zeros. We are making some progress towards this one, but not done yet. For this, it's quite easy. We can use the delta method of DFI to prove a subconvex bound or non-trivial bound for this. But you need to introduce what's called level lowering. Without level lowering, you will not, if you just blindly use the delta method, it will not give you a subconvex bound. Okay. Okay, so now I want to say a little bit about arithmetic quantum unique ergodicity. The reason is that it gives rise to two problems, which are kind of the central problems in the field in the field of analytic theory of automorphic forms, and which we hope one day can be tackled using this delta method approach. So what is the quantum unique ergodicity? You look at a holomorphic cusp form on the upper half plane. So it's a function f from on the upper half plane. To this, you can associate and measure on this modular curve, right? H modulo SL to Z. Right? So suppose that this form has weight k, right? And the measure is defined in this way. So if you take any function on x01, then mu f phi is given by phi z integrated against this density function mod fz square y to the power k times the usual hyperbolic measure, right? So that's the measure associated with f. And so if you take a subset of x01, then the measure of that subset is given by this integral. So the density function integrated over that subset. And the famous conjecture of Rudnick and Sarnak is that if you look at the discrepancy, so you start with that measure and you divide by mu f1, so you are making it a probability measure. And this is the usual probability measure that comes from the hyperbolic measure that you have, right? Then the conjecture says that as k goes to infinity, as the weight tends to infinity or the spectral parameter tends to infinity, this measure will converge to the usual hyperbolic probability measure. And there is a corresponding statement for mass forms where the parameter, spectral parameter goes to infinity. As is stated here, this statement has been proved by Holowensky and Sundararajan in 2010 and has been extended later also. But the following effective version is not known. Okay? So if you assume Riemann hypothesis for certain L function, then you can show that this discrepancy is actually going to zero quite rapidly, like k to the power minus delta, where delta can be taken as 1/4 or something. Okay, but that is not known. There is no power of the decay rate is not known to be a power of k. Okay, so this is what we want to prove. Right. So what are the analytic problems that come up from what are the problems that you need to solve to solve the QE? So there are two different ways to do the QE. So the thing is, the idea is that you can take a basis for the collection of functions that you have over here, and you try to prove this for that basis functions, right? So one such basis are given by the incomplete Poincare series or Eisenstein series, which are defined in this fashion. And the measure, then mu f of the Poincare series, you can easily compute by unfolding, So this is by definition is the measure of the Poincare series. You use it for unfolding. And then it turns out, gives you a shifted convolution sum, right? So you open up f, and when you do the integration over x, this EMX gives you a shift. Okay, so you are left with a shifted convolution sum, lambda fn plus m, where the length of the sum is the weight k, and the shift is just bounded. Okay, it can be 1 or 2 or something like that. Okay, so and you see that so to prove the QB conjecture over here, what you need to show is that this goes to 0. So if you take phi to be a Poincare series over here, mu phi is 0. So to show that this difference is going to 0, it's enough to show that mu f phi is going to 0. So mu f phm is this, and you have to show that this goes to 0. So now if you use the trivial bound for the Fourier coefficients over here, then you're stuck at the bound k to the power epsilon. But if you have a non-trivial power saving over here, like if you can show that this k to the power 1 minus delta, then this is bounded by k to the power minus delta, and it's going to 0. And you get an effective QE. So the QE problem using the incomplete Poincare series can be reduced to a shifted convolution sum problem. So the difference of this one and the shifted convolution sum problem tackled by Dickfeld and Ivanich is that there is no uniformity in this result with respect to the parameters of f. Whereas here, you are asking for an uniformity with respect to the parameters of f, because f is of weight k, which is the length. Okay, the other way is to use, for phi, you use holomorphic or mask cusp forms and Eisenstein series. And in that case, so for example, suppose phi is a cusp form, then again, you want to show that mu f phi is going to 0. There's a famous formula of Watson, which shows that this is related to the central value of a triple product L function, okay, f cross phi. Okay. And so using Starling's formula, these are completed L functions, so there are gamma factors appearing in that. So use the Starling formula to estimate those gamma factors. Then you get that this measure is bounded by k to the power minus 1 plus epsilon times this L half sim square f cross phi. So now, if you look at this L function, f has weight k, sim square f cross phi will have conductor k to the power 4. So there will be, so this is actually a GL3 cross GL2 L function. So it's a GL6 L function. And so there are 6 gamma factors, and 2 of them will not have k involved, and the remaining 4 gamma factors will have k involved in them. And so the conductor of this is k to the power 4. And so the convexity bound of this is like k to the power 1 plus epsilon. If you put the convexity bound, you are stuck. You get the bound that it's k to the power epsilon. Right? You want to show that this goes to 0, so you want to prove that it's bounded by k to the power minus delta for some delta positive. Now, if you have a subconvex bound for this, then you are done. Okay, so the QE problem through Watson's formula is related to the subconvexity of a GL3 cross GL2L function. Right, so this is the summary. So in one hand, we have the shifted convolution sum problems.
Ritabrata, so, we have about 2 minutes left.
Oh, sure. I'll just rush here. Okay, so yeah, so this is the weight aspect, and there is also a level aspect shifted convolution sum, where f is taken to be a GL2 form of level Q, and the shift is also by Q, and you want a non-trivial bound for that. And on the other hand, using Watson's formula, you can relate it to the subconvexity problem, and by approximate functional equation, the subconvexity problem boils down to getting non-trivial bounds. So it's again a correlation problem, where the length of the sum is square root of the conductor of pi cross f. Okay, then the main problem in proving the subconvexity here is that there is a massive drop in the conductor of the function of the form, and so it becomes a very hard problem. Okay, so now using the delta method, we can make some progress. For example, if you look at the shifted convolution sum in the level aspect over here, and if you take Q to be, instead of Q to be a powerful level, for example, if it is a prime power level, say Q is P to the power J, then you can get an power saving in the bound for the discrepancy, right? But unfortunately, this is already known through a different proof of this was given. Different proof of the QE problem for powerful level was given by Nelson, Pitale, and Saha. So this gives you a different proof of the effective QE for powerful level, but not a new proof. Okay, so now the main thing is to get subconvexities for GL3 cross GL2L function, and using the delta method, we can prove subconvexity in some aspects. The starting point, of course, is to just fix pi and f and prove subconvexity in the T. That was done a few years back. And the same method works when you look at the twists, or you're looking at the spectral parameter, or when you put prime power level in both pi and f, or a prime power level on pi and fix f. Yeah, I just wanted to focus on this particular theorem. So where pi is a SL3Z Hecker mass form, but is fixed. F is a holomorphic or a mass new form of level P to the power J, where J is greater than or equal to 2. So it has a prime power level. And then in this case, for this, we'll have a subconvex bound. Okay. And the proof is again via a delta method. So by approximate functional equation, it boils down to getting non-trivial bound for this. And you apply delta method, you separate the oscillation of AN from the oscillation of lambda n. So AN are the Fourier coefficients of pi. So it looks like this after applying the delta method, then use Voronoi summation formulas. And if you keep track of the saving, you'll see that this is how much you save. And the last step is applying Cauchy and opening up the absolute value and applying Poisson summation again in the outer sum. And in this way, we get a non-trivial bound because ultimately the saving over here in the last stage is p to the 13/4, which is larger than p to the power 3, which is the bound that you need to cross. Okay, so that's how you can get a subconvex bound. The main thing over here is that since f is ramified at the prime p, and since you are doing a level lowering, you need to do a level lowering. You are going modulo p over here. So both lambda here, the form is ramified at p, and also the character is ramified at p. So the Voronoi summation formula is not that easy because this is like p cubed, and this is p. So neither p cubed doesn't divide p, and p cubed is not co-prime with p. So that's why it's problematic. But still, it can be done. You need to show some pseudo character sum has square root cancellation, but that can be done. Okay, so with that, I'll stop. Thank you.